welcome. So, in last few classes we looked into fundamental subspaces associated with a matrix solution A x is equal to b, and we also looked into orthogonality between row space and null space, column space and left null space. So, what we learned from there, that left null space is orthogonal to column space and row space is orthogonal to null space. The idea that left null space is orthogonal to column space is important to realize the fact that if the right hand side vector b has some component in left null space, this vector is not a member of column space, and therefore, we cannot solve A x is equal to b. A x is equal to b is only solvable when b is a column space vector. So, if b has some component in column space, we cannot solve A x is equal to b, and in many cases we end up in situations where we have seen earlier where A x is equal to b equation is given, but b is not in column space, especially when we have independent columns, but the columns are not spanning the entire R n, and b is a member of R n which cannot be found by combining given column vectors of the matrix A. So, we say that there is no solution, but especially in optimization, in the area of optimization we have to deal with situations when we get a number of equations, the equations do not have a particular solution. And why it does not have any particular solution? Because the columns of this equation is not spanning the entire column space R n or R m, and the right hand side solution vector b is away from the column space. However, when we are optimizing it, for example, say we got certain observations from experimental methods and formed the equation. Now, we are seeing that the right hand side matrix B is not in the column space. So, we cannot solve this equation, but in practical cases, especially for engineering applications or when we do something like data science, we end up in situations when we need a solution, however, the solution does not exist. So, for example, I am trying to design a particular surface, and for designing the surface I got equation for normals at few edges of the surface, and now I cannot solve those equations. Once we can solve this equation, I can get the coefficients which will be multiplied with different splines, and I can design the surface. However, I cannot solve this equation. I am in a situation. Why I cannot solve this equation? Because I do not have enough columns to span the entire vector space R m, and B lies in a space which is not in column space of R m. So, what we do there, especially in engineering applications, we say that we will try to find out an approximate solution. That means that the solution will not be correct. I will not find out any x which will satisfy A x is equal to b. Of course, I will not find any x because b does not lie in column space of A. So, I cannot represent b as combination of columns of A, or I cannot write x is equal to b. So, I will be in a situation where I cannot solve A x is equal to b. However, we will try to propose some estimate of x which will not satisfy x is equal to b. So, when we will write A x that is not is equal to b, or b minus x has some error, x is not exactly equal to A, not exactly the solution of A x is equal to b, x an estimate of the solution of x is equal to b, and therefore, it has some error, and we will try to minimize the error. And what we call, we will find out what is the best estimate for x in case of the equations A x is equal to b, when the equations does not have any particular solution. And in today's class, we will look into this type of equations, and the main idea is that if b does not lie in column space of A, we cannot solve A x is equal to b, but there can be some component of b which is on the column space of A. So, we will take the b vector, we will project it into the column space of A, and for that projected part of b vector, which is b c lying in the column space of A, we will solve A x is equal to b, and we will get a solution x. We will say that this is the best estimate of x. Why is it best estimate? Because we will also show that this estimate reduces or minimizes the error between b minus x. So, we will discuss this in this particular class. So, this is on best estimate and normal equation. Normal equation is the equation which will solve we cannot solve A x is equal to b. In lieu of A x is equal to b, we will solve a normal equation form of A x is equal to b. Let us see what is that. So, we go back to the fundamental theorem of linear algebra, which says that in R n the row space exists and in R m the column space exists. That means, there are n number of columns. So, each row has n elements, there are m number of rows, each column has m elements, and row space has a dimension r, which are the number of independent rows, and it is same as the dimension of column space or number of independent columns, and n minus r is the dimension of null space. So, if all the rows are not independent, then n minus r is the I am sorry, if number of independent rows is less than the order of the vector space R n, then n minus r is the dimension of the null space. So, if all the rows do not represent a basis of R n, there are some dependent rows, and n minus r will be the based on the dependency of rows will be the dimension of null space. Any solution x n in the null space when multiplied with the vector with the matrix A goes to origin 0. So, x n is a null space and x r, which is the solution of the equation x is equal to b, must lie in the low row space, because whichever does not row space is orthogonal complement of null space, whichever does not lie in null space must lie in row space. So, I take x r, which is a row space vector. X r is linear combination of rows of A, multiply it with the matrix A, I get a column space vector B, and I take another vector x n, which is not a row space vector, which is a null space vector, but in R n I multiply it with A, I get a 0 vector. So, I add them and I get the final result A x is equal to b, where b is a column space vector. B is a column space vector, means B is a vector in the subspace of dimension R, which is formed by R independent columns, wherever columns are belongs to the vector space R m. So, if there are R independent columns, R is not equal to m. So, m minus r will be the dimension of left null space, and there is, if m minus r is non-zero, there is a possibility that we can get some vectors, we can think of some vectors, we can propose some vectors which do not lie in the column space. In case m is equal to r, left null space is only the 0 vector. So, there is nothing on 0 left null space, but otherwise there can be something on left null space which does not lie in the column space, and therefore, if we get a b which is lying in the left null space, we cannot solve A x is equal to b. So, one important observation is that every matrix maps its row space to column space, and this mapping is invertible. In a sense, if I have A x r is equal to b, if b is in the column space and b belongs to the column space of A is always invertible, and I can write x r is equal to A inverse b. And we have seen that this if A is a rectangular matrix, we will think of a left inverse, but this has to be there. The row space and column space are 1 into 1 mapped, and this mapping is invertible if b lies in the column space. Similarly, x n is in the null space. So, x n is equal to 0 is the 0 vector, and A x is equal to x n plus x r is equal to b plus 0 is b. So, x n lies in the null space, x r lies in the column space, and the final solution x is addition of row space and null space. So, it is anywhere in R n, it might not be in the row space if null space is non-zero. This also will map to x is equal to b. However, this mapping is not invertible. If I try, because there are infinite, if null space is non-zero, there can be another null space solution. So, this can be also another x n 1, which is similarly giving us A x n 1 x n 1 is equal to 0, and we can get another solution x is equal to x r plus x n 1, and this A x is also b. So, there are infinite number of x's if null space is non-zero, which is giving me x is equal to b. So, this mapping is not invertible. This mapping is not invertible simply because this is not 1 to 1, this is a many to 1 mapping. However, AXR is equal to B, this is always an invertible mapping. Anyway, we now try not to look into the left part of this diagram, that what happens to row space or null space. Rather, we will try to see if B does not lie in column space. If B is away from the column space, what will happen to the system of equations. So, we have a similar situation. However, B lies outside the column space. So, we cannot have any vector in row space x r which multiplied with A gives me x r is equal to B, because B is outside the column space. So, A x is equal to B does not have any solution. B can be decomposed in two components. One is along the column space. So, we project B along the column space and we get a vector B c. So, this becomes B c. This is the vector sorry. Like this. So, this is projection of B on the column space, and we can also make a projection in the left null space, and this there will be another vector B l n which is in the left null space. So, B can be decomposed into two vectors, one is its projection in the column space, another is the perpendicular part which is its projection in the left null space. And this is possible because column space and left null space are mutually orthogonal spaces in R n, and they are orthogonal complements of each other. If something does not belong to column space, that must belong to left null space. So, nevertheless, B can be decomposed as components in column space as well as in left null space. The component of B in column space is B c, and this can give a solution A x is equal to B c, right, because B c is a column space vector, and now I can have solution of A x is equal to B c. And what we will do here, that we will call that this solution, this x, as the best estimate of solution of A x is equal to B. A x is equal to B c, the solution of that can best estimate the solution of A x is equal to B. That will be the proposition here. There will be no solution for the left null space. Of course, x is, if B is in left null space, there is no solution. These components B c and B l n can be found by projecting B into the onto the spaces. So, if B lies outside the column space, then there can be two components of B, or B can be decomposed into two components. One is its projection in the column space, another is projection on the left null space, which is orthogonal to column space. For left null space B, projection of B or B l n A x is equal to B l n really does not have any solution, because B l n is completely away from the column space, it is orthogonal to column space. The projected part of B onto the column space A x is equal to B c will have a solution. For any B, for any right hand side vector which lies in the column space, A x is equal to B will have a solution. So, A x is equal to B c will have a solution, and this solution we will call this as the best estimate of the solution of A x is equal to B, which is not solvable. A x is equal to B is not solvable because B is not on the column space. We project B into the column space and get B c. Ax is equal to BC becomes solvable, and this solution is the best estimate of the solution of x is equal to b. And we will go ahead with this, that now. So, now our target will be to find the solution x is equal to B C and to find the projection of B on column space B C. And we also have to justify why are we telling it to be best estimate, whether this is the least error minimal error solution of x is equal to b, or if I try to write b minus x, that will not be 0 obviously, because x is not equal to b. We are solving x is equal to b c, we are not solving x is equal to b. So, b minus x will be some value, we call it error. Is it minimum if we do it in this way? Let us look into this. So, how to find this best estimate of x is equal to b when b is not in the column space? We will try to solve Ax tilde is equal to B C, where B C is in the component of B in column space, or B C is the projection of B in the column space. B C is obtained by projecting B onto the column space. So, we have a matrix B, we project it into the column space and we get Ax tilde is equal to B C. Why? Because there should be some B C is in the column space. So, there should be some x tilde which is some value which is coefficients which is multiplied with the columns of A, and the linear combination will give us B C, or we can write any column space vector. So, any column space vector, any vector in column space is of the form of Z, or rather I will write A Z is of the form of so column of A multiplied by Z 1 plus column of first column of A multiplied by Z 1. So, what is A Z? This is like A 1 1, A 2 1, A 3 1, A n 1, first column multiplied by Z 1 plus A 1 2, A 2 2, A n 2 with Z 2 plus so on. So, any column space vector will be of this form. So, when B is projected to the column space, we should get some x tilde, for which we can write x tilde is equal to B C, because this x tilde vector each component is multiplied with each component of A, with each column of A, and linear addition will give me a column space vector B C. Okay. So, now if I try to solve this equation, x tilde is called the best estimate of for x is equal to b, and b minus x becomes orthogonal to column space. Ax tilde is on the column space, what is, or B C is, rather B is the vector which is inclined to column space. So, B C is its projection to column space. Therefore, B minus B C is the part which is perpendicular to column space. We think of taking a vector 2 I plus 5 j. So, 2 I is the component along x direction. So, this is 5 j which is perpendicular to x direction. Therefore, B minus B C, if B C is along column space, B minus B C is perpendicular to column space, or B minus x is the component, as B C is equal to x tilde, B minus x tilde is the component which is orthogonal to column space, as it lies in the left null space. That means, any vector which is perpendicular to which lies in the left null space must be orthogonal to column space. So, B minus Ax is orthogonal to column space vectors, or it is orthogonal to all columns of A. So, we can write A transpose B minus Ax, dot product of B minus Ax with all the columns of A must give me a 0 vector. each column is dot product of A with each B minus X with each column of A must be 0, because B minus X is orthogonal to the column space of A. So, it is orthogonal to all vectors of the all column vectors of the matrix A. So, we multiply A transpose with B minus X, we will get zeros as the row of the solution vector. So, it is a 0 vector, and with some modification we get like with rearranging it, we get the equation A transpose A x is equal to A transpose B, and this we call as the normal equations. So, earlier we had an equation A x is equal to B, which is not solvable. We propose that we will not solve for A x is equal to B, rather we will solve for the component of B which lies in the column space, which is the projection of the column space, and the equation for that is of course not A x is equal to B, rather it is something else, and this equation we obtained as A transpose A x tilde is equal to A transpose B, where x tilde is the best estimate of x, and this equation A transpose A x tilde is equal to A transpose B is called the normal equation. Now, we have to see that whether this equation is solvable. That means, A transpose B should lie in the column space of A transpose A. B does not lie in the column space of A transpose A, and we obtain that through just projecting B in the column space of A. So, it is ensured, and we also have to see that if this equation is solvable, then some process like Gauss elimination should hold, and we should not get a 0 pivot when doing Gauss elimination or LU decomposition type of things. So, A transpose A must be a non-singular matrix, or A transpose A must be invertible, and we look into it that left inverse of matrix A is given as B is A transpose A inverse A transpose, where what is left inverse? The inverse, the matrix which is multiplied in the left of matrix A gives an identity matrix. Left inverse exists if the matrix has full column rank, that is, or the matrix have independent columns. So, if the matrix have all independent columns, then the left inverse will exist, and if left inverse exists, that means A transpose A is invertible, otherwise left inverse will not exist. So, if we get a matrix which has A which has all independent columns, then A transpose A is invertible, or we should be able to get a solution of A transpose A x is equal to A transpose A x tilde is equal to A transpose B, or x tilde can be obtained as A transpose A inverse is equal to A transpose B. So, what we can write is that A x is equal to B, we have seen when the left inverse exists, A x is equal to B has at most one solution if columns are independent as well as spanning, then A x is equal to B has just one solution, but A x is equal to B has at most one solution if columns are independent. It may not have any solution, but if it has any solution, it will have at most one solution, it cannot have infinite solutions if the columns are independent. And in that case, then A transpose A, then if this has at least one solution, then A has left inverse and A transpose A is invertible. So, we have a matrix which has independent columns. Now, A x is equal to B is not solvable because these columns are not spanning entire Rm and B lies outside the column space. Still, we can have an estimate of A x is equal to B, which is A transpose A x tilde is equal to A transpose B. And this equation is solvable because matrix with independent columns will have A transpose A to be will have A transpose A which is invertible. Now, what we will check is that this equation system gives we will check that this equation system gives a least error solution of x is equal to b, but before that we once also check this, that what will be null space of A transpose A. So, if A transpose A is invertible, what we understand that null space of A transpose A must be 0, but let us see how what will be in null space of A transpose A. Null space equation gives us A transpose A x n is equal to 0, and null space equation of the matrix x n A is A x n is equal to 0. So, if I substitute, if I multiply this with if I multiply this with A transpose A x n is equal to 0, and we get A transpose A x n is equal to 0. So, this is also the solution of first equation. So, A transpose A and A has some same null space. So, this should be pondered over at a later stage, that if A has independent columns. So, but A does not have all independent rows, therefore, there should be some null space of A, and how this is related with null space of A transpose A, but A transpose A and A will essentially have same null space, which is evident here. Now, what I was telling earlier, that we have to check that the best estimate is actually a best estimate, that means the error obtained while doing finding best estimate is minimum, and we can check that normal equation gives least square solution. Instead of normal equation, if we do a least square method, do least square, find least square of error and try to find out the solution which gives least square error solution, it will be the same one. A x is equal to b has no solution. So, we let us estimate x as x e, and the error e is a x e minus b. So, the squared error is e square, which is, and we try to find out the squared error in many cases, because it is an absolute value, which is a x e b transpose a x e. So, this is a vector transpose a vector. So, it is a scalar. This is the sum of the error in each of the rows of A, and if I try to minimize it, then we will get the equation d square d x e is equal to 0. So, of course, we have to see that the second derivative is positive for minimal value, but then we find out A transpose A x is equal to A transpose b, which is nothing but the normal equation. So, we can then that shows that normal equation is also the least square equation, and the error is minimized when we are solving normal equation, and that is why this is a term used by statisticians, that A transpose A x tilde is equal to A transpose b is the best estimate of the solution of x is equal to b when x is equal to b does not have any solution, or b lies outside the column space. So, look into a example quickly before we finish. Take the matrix A is 1 1 0, B is 2 3 0, B is 4 5 6. So, you can quickly check that these are zeros and this is non-zero. So, the column of A does not have a 0 and the third component, B has all non-zero third component. So, B really does not lie in column space of A. B is an independent vector of column space. Okay. So, we find out A transpose A, which is 2 5 5 13, and A transpose B is 9 23, and A transpose A x tilde is equal to A transpose B, which gives us x 1 tilde is x 2 tilde is equal to 2 1. So, this is the what we will say that this is the best estimate of x is equal to b. This is the best estimate, and this comes from solving the normal equations. So, you just substitute A transpose B here, substitute A transpose A here, and we can solve this, because there is a 2 by 2 system, we can quickly check it also. Now, what we will do, we will substitute this x into this x tilde into the main equation and see what is the error. So, A x tilde, and A x tilde is the projected value of B in the column space, is B c, is A into x tilde is 450. The columns are 1 1 0 2 3 0. So, this is basically projected value. B vector was not in column space, and B c is projection of the B vector in the column space. So, column space here was 1 1 0 2 3 0 means 2 vectors like this, right, which is forming the a particular plane in R3, and this is the this is R3, this we should not use here, and the vector B was away from the R3, this is B, and now we project B in this column space, and this becomes B c, which has a 0 component in the z direction. So, this is a projection of B in column space, it is verified. So, in next class we will start looking into detail on the projection operators and what are the general forms of operator which can project a vector B onto the column space, and we will explore detail about the projection process. Thank you.